All right, good morning, ladies and gentlemen. Better late than never, I guess. So we were talking about ways of releasing renin. That's where we found ourselves on Thursday. How we're going to release renin. We saw that renin came from changing pressure in the afferent arterioles. Renin can come from the SNS innervation that occurs in those arterioles releasing, and efferent arterioles releasing renin. And then also this thing that we talked about, sodium chloride in the distal tubule in the macula densa. Okay, so what did all that mean? So then we talked about what was the macula densa, where were we finding it? Okay, and we were talking about, let me run a pen here. We were talking about how the distal tubule, anatomically, the distal tubule will curve back up to be in close proximity to the afferent and the efferent arterioles. Thanks, Ross. The afferent and the efferent arterioles, okay? So that cells lining the distal tubule are releasing products to affect those afferent arterioles. Okay, essentially is what this juxtaglomerular apparatus is. Cells of what we're going to call the macula densa. So those are just cells lining the distal tubule on the side that is intersecting with the afferent and the efferent arterioles. Okay? So based on the sodium and chloride in the macula densa, then, these cells are going to respond to that, release products to then affect renin-releasing cells of the afferent arterioles to cause a change in renin. Okay, so that's where, let me get that back here. We're talking about delivery of sodium chloride to the distal tubule to the macula densa. And when the sodium chloride in the macula densa goes down, renin goes up. Okay? So when the sodium chloride goes down, renin will go up. When sodium chloride in that macula densa goes up, renin drops. Okay? And it's all just communication between those two cell types. Okay? So then the game afoot is, how do you change sodium chloride in the macula densa? Okay? So what's happening there? Let's take a look. All right, let's think about how we change sodium chloride in the macula densa, because then that's going to link it all for us. So, how do we change sodium chloride delivery? To the macula densa? We change tubular flow. Okay? It's all going to be about how long we spend equilibrating in that thick ascending limb. Right? That thick ascending limb had those symporters. Took out sodium chloride. So the longer we stay there, the less sodium chloride we have. Right? So if flow slows down and we spend a long time there, we're going to take out sodium chloride, and in the early distal tubule, that macula densa, we're going to have less sodium chloride. If we flow really quickly by the thick ascending limb and by those transporters, we're not going to take as much sodium chloride out, and more sodium chloride is going to then arrive at the cells of the macula densa. Okay, so it all comes down to what is the flow in the tubule, and especially what is the flow in that thick ascending limb. Okay, so the game we're going to play is how we're going to change tubular flow. Essentially, tubular flow was a function of glomerular filtration rate. Right? The more we filter, the more flow we get. Right? Okay, so tubular flow is going to be a function of GFR. Okay, so let's go through an example. Let's say I were to increase GFR. And we've been doing this a lot, right? Anytime we change pressure in that glomerulus, we change filtration, we change GFR, we're going to change tubular flow. Okay, so we've been messing with this a lot. So if I increase GFR, I'm going to increase tubular flow. Okay, and this is going to decrease my equilibration time. Especially important here is that this will then decrease the time spent in the thick ascending limb. Of that loop of Henle. Okay, and why do we care about that? Because that's time spent by our sodium chloride potassium symporters. Okay, so if I were to increase tubular flow and I drop time spent there, I'm going to decrease the amount of sodium chloride reabsorbed. Okay, so if I didn't move it from the tubule into the interstitial space, then it's still in the tubule. And increase that sodium chloride in that tubule. And then that volume or that fluid is now going to flow by the early distal tubule where the cells of the macula densa are. Okay, so this is going to result in an increase in sodium chloride at the macula densa. Okay, and we saw from that other page the relationship between sodium chloride in the macula densa was related this way. If I were to increase sodium chloride at the macula densa, that means I'm going to drop renin. So a couple of things are going to happen here based on this GFR. So the first thing, in terms of what we've been focusing on, we're going to decrease renin. What did renin do? So renin was the kind of catalyst for producing angiotensin II and aldosterone, all that kind of stuff, right? But very locally then, this will decrease local angiotensin II production, right? So remember, we always had that angiotensinogen, that precursor floating around. We have renin produced. And then we did say that on cells of the afferent and efferent arterioles was the ACE enzyme that converted angiotensin I to angiotensin II. Okay? So all of that would happen right here. Okay? Change sodium chloride in the macula densa. We drop the amount of renin produced by these cells. We would then decrease the amount of angiotensin I, which would then decrease the amount of angiotensin II. Okay? So that's that relationship. Decreased local angiotensin II, so therefore I'm going to vasodilate. What did we say local angiotensin II did? Vasoconstricted efferents over afferents. So now I'm going to vasodilate efferents greater than afferents. If I vasodilate efferents greater than afferents, I've got more volume going out of the glomerulus, decreased pressure in the glomerulus, decreased GFR. Okay? This maneuver, this local angiotensin II, let's think about that for a minute. we did say that local angiotensin II caused a vasoconstriction of efferents over afferents. Okay, but then we said systemic, whole body angiotensin II caused a vasoconstriction of afferents and efferents equally. Okay, so this gets difficult to produce, right? Because really the only way that we can get afferents and efferents arterioles to even respond to angiotensin II is to have a membrane receptor population, right? So how can we get afferents and efferents to respond differently? I guess we could have more membrane receptors on the efferent arterioles. That way we could get local angiotensin II to affect efferents greater than afferents. But then whole systemic angiotensin II should affect efferents more as well, and that didn't happen. We could invent a whole new membrane receptor and say, okay, well maybe the efferent arterial membrane receptor is a little bit weird, maybe it's a little more potent or something. But you still can't get this thing to happen where local angiotensin II would cause an effect on efferents, but systemic angiotensin II would cause an effect equally, right? So the thought here is that it's all anatomical, in that when I produce renin in the efferent arterioles, and I produce angiotensin I, and I convert it to angiotensin II, by that time it's been flowing downstream, and the only vascular bed that gets affected by that local angiotensin II is the efferent arterioles, because it's renin here, not angiotensin II. And that by the time you go through all that cleaving and et cetera, that has to have happen, that by the time you flow that downstream, you have angiotensin II, but now it's only on the efferent arteriole side. Okay, so it's thought to be an anatomical thing, right? That we don't have different membrane receptor populations for angiotensin II or different sizes of membrane receptor populations, that it's only because of a delivery system, right? We produce renin here, and then by the time remember renin was converting angiotensinogen to angiotensin I. We didn't have any biological effects of that. So we might have angiotensin I showing up here, but then as we flow it downstream, it gets converted to angiotensin II. And by the time it shows up here, it's angiotensin II. And so now we get an effect of angiotensin II here, because that's where it's showing up, okay? So this is local effect of angiotensin II. It's more like on this side of things, afferent arterioles would have constricted if angiotensin II was there, but it wasn't. Renin and angiotensin I was there. And then by the time we get those into the mix and flow them downstream and create angiotensin II, it just happens to be beside an efferent arteriole. Okay? So we can now say things like, especially because of this juxtaglomerular apparatus, I'm going to get a drop in renin, a drop in local angiotensin II that's found itself by the efferent arterioles. So now I'm going to vasodilate those efferent arterioles greater than the afferents, and I'm going to affect GFR. But if the whole body has angiotensin II in it, we're going to find angiotensin II on afferents and efferents, and they will constrict equally. Okay, so the game afoot with angiotensin II is to know, are we just talking local here? Because we're going to affect GFR. Or are we talking systemic here? Because then we're going to affect both afferent and efferent equally and not affect GFR. Okay? When it comes to sodium chloride in the macula densa, it's all local. It's all small or local concentrations, low concentrations that they'll talk about. So we get this effect on GFR. Okay, so that's essentially what that means. Okay, delivery of sodium chloride by the distal tubule to the macula densa will drop angiotensin II, or sorry, renin. Okay, well, that makes sense. But if we continue on with our example here to try to think about what would happen if we had an increase in GFR, increased tubular flow, decreased equilibration time, and we get an increase in sodium chloride showing up in the at the macula densa, we would get that drop in renin. Okay, that's totally for real. There's also the second thing that's going to happen. We're going to increase afferent resistance. So we're going to vasoconstrict afferents. This will essentially drop pressure in the glomerulus and decrease GFR. Okay, so this is basically saying that if I drop sodium, oh, where's my picture? If I drop sodium chloride in the macula densa, there's a second system happening where these cells release a vasoconstrictor that will affect afferent arterioles. Okay, so there's something else happening down here as well. It's thought to be adenosine, but nobody really knows. Okay? Let's just write that out here. So we've got a vasoconstrictor released. Okay. It's thought to be adenosine. Adenosine is an odd choice, which is why people are questioning it. Adenosine is usually a vasodilator. Everywhere else in the body, it's a vasodilator. But it looks so far, the data seem to support adenosine here as a vasoconstrictor. So we've talked about this phenomenon before, almost I think on day one, where we talked about flow through the tubule, and we called this tubuloglomerular feedback. Okay, so take a look back in your notes early on where we left a placeholder for this thing called tubuloglomerular feedback. Tubulo, the tubule, is feeding back information to the glomerulus. Tubuloglomerular feedback. Okay? Okay, so take this information back there, bring that information forward here, because that's where they connect. Okay? So we've seen this before. We've also been controlling GFR through autoregulation, right? If you go way back into the notes, we showed how your classic myogenic response, stretch causing constriction, that if we had an increase in GFR, we would increase resistance to drop GFR. Okay, and you can see in this scenario, we have built two very local ways at the kidney that if GFR went up, that we would drop GFR back down to normal. Okay, there is an incredible control on glomerular filtration rate at the level of the kidney. Incredible local control here. Okay, and if we look at the numbers, we'll see why it's extremely important to keep GFR constant. Okay, GFR, our glomerular filtration rate. Remember how much flow went to our kidneys. About a fifth of all of our blood flow in any minute was going to our kidneys in the first place. So a huge amount of flow is directed there. The glomerular filtration rate is approximately 120 mils per minute. Okay, that's approximately 7.2 liters in an hour. I need you to think about that number for a minute. 7.2 liters are filtered into your kidney per hour. Per hour. 7.2 liters. Per day, 172 liters per day. So every day that you get up and walk around, your kidneys have filtered 172 liters of fluid. You do not want something going wrong with your kidneys. 172 liters per day. Okay? So then let's say you were sitting down and standing up and sitting down and standing up, maybe that was part of your job a lot during the day, you could actually change GFR a fair amount during the day. Let's say, even if we were to increase GFR by 5%, okay, so that means I'm going to filter an extra 8.6 liters per day. Okay, so just by changing GFR by 5%, small amount, the amount that your kidneys now have to handle is 8.6 liters more. Now we know that 70% is going to be obligatory, the reabsorption is going to be obligatory, right? So 70% of that is going to go to that proximal tubule and it's going to be reabsorbed. So that's a good day. So 70% is reabsorbed by the proximal tubule. That obligatory reabsorption, so that's about 6 liters. So the proximal tubule will get us back the extra. But the problem then is a 30% of that 8.6 liters is now heading into the loop of Henle, the distal tubule, and the collecting duct, and is now completely, whether we get it back or not, is completely dependent on ADH status. Okay? So 30% went into the loop of Henle, distal tubule, and the collecting duct. Okay, and that was to the tune of 2.6 liters per day. So depending on what your ADH status is, you have the potential to lose an extra 2.6 liters a day just by messing with GFR by 5%. Okay, massively powerful tool. So we have a huge amount going on at the level of the kidney to try to keep GFR constant, right? Local renin release, tubuloglomerular feedback, and the autoregulation that we're doing down here already, all trying to keep GFR constant. But on top of that, if we had a blood pressure problem, we would want to lose volume to help solve the blood pressure problem, right? So this is why I think that there is so much hormonal control at the level of the kidney, right? It's all controlling afferent and efferent arterioles are a sum of the pluses and a sum of the minuses. And if you've got all of this trying to keep GFR constant, you had better throw the kitchen sink at it. If you want to get GFR off by just like 1%, so that you can now use GFR or use the kidneys to help fix a blood volume problem. If you've got an increase in blood volume, increase in blood pressure, we want to increase GFR to filter more. But we got all this going on to keep GFR constant, right? So I think that this is why not only when you bring one hormone out to help, you bring like 4. So that's why you have this renin, angiotensin II, aldosterone, ADH system, because you better start throwing the kitchen sink at this thing just to get GFR to budge by 1%, and that'll do. Right? You don't have to budge GFR by much in order to help us with a problem, okay? All right, so let's map that out a little bit. Try to draw the relationships together. That's what this guy is here really trying to do. He's trying to think about our local and central effects of what we got going on. So we'll run through an example. Let's say we were to increase mean arterial pressure. So we'll start here. Okay. Problem is an increase in mean arterial pressure. We would then have an increase in pressure in the glomerulus based on that. Increase volume into increase volume in, increase pressure in, so that volume in, volume out argument. Okay. Increase pressure in the glomerulus, we would have an increase in filtration based on that, so we've got an increase in GFR. Okay, that increase in GFR would increase tubular flow. decrease equilibration time, right? Decrease the amount of sodium chloride removed from the tubule. So we've got more sodium chloride in the tubule. Increase osmolarity at the macula densa, right? So that's that increased sodium chloride at the macula densa. All right, so the response to that would be then, because of this relationship of sodium chloride in the macula densa and our renin, increase in sodium chloride in the macula densa, we would drop renin, decrease our local angiotensin II, vasodilate the efferents, or decrease the resistance of our efferents. Okay, so I vasodilate those efferents. That's going to result in a decrease in pressure in the glomerulus, the glomerular capillary bed, and decrease GFR. Okay, so this is the kidney locally protecting GFR. Okay, so that was that whole sodium chloride in the macula densa we just talked about. Okay, so local kidney defending GFR. Because of that change in osmolarity at the macula densa, then we now know we've got this vasoconstrictor hanging out. Okay, so that means I'm going to increase the resistance of our afferents. So that's that vasoconstrictor that we just talked about, tubuloglomerular feedback. Okay. Increase the resistance in our afferents is going to result in a decrease in pressure in the glomerulus and a decrease in GFR. Okay, again, the kidney locally trying to defend GFR. And then I want you to go back in the notes and bring forward this idea of the myogenic response. We called it autoregulation, where an increase in pressure would cause an increase in stretch, increase resistance to keep flow constant, to keep GFR constant. So bring that idea forward here too. And you'll see what the kidney does is ×3 trying to keep GFR constant. That's what the kidney's job apparently is. Keep GFR constant, okay? But if we have a problem with mean arterial pressure, then we could use changes in GFR to help us out, right? So we do know that if we did have an increase in mean arterial pressure, then let's say this was due to an increase in blood volume. Okay. Then an increase in blood volume would result in atrial stretch. Which would increase atrial natriuretic peptide. What did atrial natriuretic peptide do? Vasodilated afferents, vasoconstricted efferents. Okay, and what does this do? Increase GFR. Okay, so now you can see the system is trying to get the central system is trying to get the local system off its game a little bit, right? So it's going to start throwing in things that are pretty powerful, like atrial natriuretic peptide, to mess with afferents and efferents to try to get GFR to increase. We would like to have a little more filtration here, please, because then we could get a little more volume out of the body. And that would fix our problem. All right, so now we're just trying to tip the scales of local control of GFR just a little bit. But that one is just not going to do, right? Because we have all these mechanisms to keep GFR constant. Apparently one is not going to do. So that's why atrionatritic peptide is also related to all of those other hormones, right? Not only are we going to bring on something which increases GFR, we are going to drop other things that might decrease GFR, right? So we're going to go after, that's why atrionatritic peptide was then related to renin and then to inhibiting renin to decrease whole body angiotensin 2. Okay, so now that we've got whole body angiotensin 2 is starting to drop. Right, so when it was whole body angiotensin 2 or systemic angiotensin 2, it was a vasoconstrictor of afferents and efferents equally, right? So now we're going to, if we drop it, we're going to vasodilate. We're going to vasodilate afferents equal to efferents. This now will start to minimize this local effective angiotensin 2. The local effective angiotensin 2 is just going after the efferents, right? Now we get the systemic stuff on board, and we start to affect those afferent arterioles as well. So this maneuver starts to minimize the local effects of angiotensin 2. So this is the body starting to throw the kitchen sink at the kidney to try to get GFR off its game by just about 1 or 2%. Atrionatritic peptide also inhibited ADH, all right? So ANP is now going after all these other hormones. Right, ADH was a vasoconstrictor of afferents over efferents, right? So now we're going to vasodilate afferents greater than efferents. Vasodilating afferents greater than efferents is going to increase GFR. We had an effect on aldosterone, which is going to affect sodium balance and water reabsorption. Okay, but you can now see why I think we require excuse me, so many hormones to regulate this kidney, because it's so heavily protecting GFR. So indeed, all of these things will be happening at the same time, right? The kidney will always be trying to defend GFR. And then we have to change atrionatritic peptide, angiotensin 2, ADH, and aldosterone to try to get GFR off its game to help fix our problem. Now, on top of all this, we can't forget that indeed, if I had an increase in mean arterial pressure, I would have sensors that would sense that, right? I would have sensors that would then result in a decrease in the sympathetic nervous system output, right? And we talked about SNS related to renin. If I were to decrease SNS output, I would decrease the amount of renin released. Okay, and so now it's systemic, the whole body. The brain is now starting to take control a little bit over what the kidney is doing. Again, another maneuver to try to get GFR off its game. But you also know that the sympathetic nervous system changes ADH release as well. Okay, so we are bringing out the big guns in terms of trying to get the kidney to stop its really tight regulation of GFR. Okay, so springing off here is the entire rest of the course, essentially, right? In terms of how we know the body is going to respond to this. right? Because you know then what the body is going to do, not only in terms of the kidney now, but you know what the body is going to do in terms of heart rate, contractility, total peripheral resistance, all that kind of stuff, okay? All right, so I think then it's worthwhile going over an example like that, where we do actually put everything together, where you actually can see everything kind of come together and get a feel for why the heck we were talking about all the stuff we've been talking about. So I will run off the answers you guys give me. If you don't give me any answers, we just won't do it today, and we'll move on to respiration. Whatever you feel like doing. Let's do an example of, let's go back to ones that are familiar to us, right? A decrease in left ventricular function. So let's say you are in a left heart attack, okay? Okay, so we've got decreased left ventricular function. So the body has no idea that you're in left ventricular function, that there's a decrease in left ventricular function, right? Because there's no sensor for the left ventricle, right? So we go to things. So the body isn't going to be perturbed at all unless you can sense something. Okay. So then, in order to know how the body's going to sense something, you got to know how the body was changed based on this maneuver. So while I draw it out, think for a minute about what's going to happen in our compartments based on this problem. All right, so the challenge is to decrease in cardiac output of the left heart. Okay, so can someone walk me through what's going to happen above, below that challenge? You pick where you want to go. Yes. Perfect. So what does the left heart do? It moves blood from the pulmonary veins to the systemic arteries, and that pump is no longer doing that. So we should absolutely expect a decrease in volume and a decrease in pressure. Okay, so that all on its own sets us up for another half hour's worth of work. We've just dropped mean arterial pressure. Okay, you know the sensors attached to that, and you know how the body's going to respond to that. But before we go there, let's just take a quick look at what the rest of the body is doing so that maybe we can tap into other sensors that we've set up along the way. Okay, so we've got a decrease in volume, decrease in pressure here. We should then, because we're no longer emptying this compartment, an increase in volume and an increase in pressure in the, excuse me, in the systemic or pulmonary veins. Okay. So I would say those would absolutely happen. So now where are we going to go? Work our way around the system. No, we don't want to work around the system. We don't have to work around the system if we don't want to. Yeah. So decrease in volume and decrease in pressure here. So how did that happen? So flow, you changed P1, right? Here, I totally buy that. Good? Now what? Yeah. because of a decrease. So that's right. So this represents a decrease in mean circulatory filling pressure. And you're going to relate venous return and filling pressure by the equation. Perfect. So we decrease mean circulatory filling pressure. We're going to decrease venous return. Perfect. We decrease venous return. So what? Decrease venous return to the right heart. What does that mean? Like decrease cardiac output. So that will result in a decrease in preload, right? Decrease end diastolic volume, decrease stroke volume, decrease cardiac output. Agreed. Okay, we're almost there. What does that mean for pulmonary arteries? Yep. And for a decrease in volume and a decrease in pressure in those pulmonary arteries. Brilliant. Okay? Yes. So you want to go from pulmonary arteries to pulmonary veins? Is that where we're headed? Okay, so we're going to get a decrease in flow there. Awesome. And you said because we decreased P1. So we decrease P1, so we're going to get a decrease in flow, so we might expect a decrease in volume and a decrease in pressure over here. Okay, so there might be a conflict, and we're totally comfortable with that because we don't know how much time we spent in this with this problem. Okay, but when we look at this now then, there are only certain things that our body is going to respond to, right? Our body really isn't going to respond to pulmonary venous pressure. We have no sensors for that compartment. Right? So when you look at this little model then, we're like, well, where do we have sensors? And what's going to tweak the body to do anything? Because if we don't have a sensor, the body isn't going to be tweaked to do anything, right? So we know we have sensors on this side, right? We know we have sensors for mean arterial pressure. We know we have sensors on this side, right? The low volume pressure receptors. We have sensors in the right heart to release H1 natriuretic peptide. Okay, so now when we look at this, I would then say, okay, let's then bust out where our sensors are, because that's how the body's going to respond. The body doesn't know anything, right? The body responds to stimuli, right? The only way it can respond to stimuli is through sensors, all right? So if I were to pick on a sensor first, I would say, I'll get us started. Let's look at those high pressure baroreceptors. Okay. Decrease mean arterial pressure, that's what we're going to be responding to. Okay, so a decrease in mean arterial pressure is going to result in what regarding our sympathetic nervous system? Increase or decrease sympathetic nervous system? Sympathetic nervous system going to be wound up by a drop in mean arterial pressure or turned down? Which way are you going to put it? Up, down, stays the same. You want it to go down? Okay, so we're going to drop our sympathetic nervous system. We're good with that? You're going to increase. Okay, so we're flipping a coin. Increase or decrease sympathetic nervous system? What do we think? How many vote for increase sympathetic nervous system? What do we got? Ooh, yeah, I guess, ooh, good, good. Decrease sympathetic nervous system. Decrease sympathetic nervous system, we have 1 or 2. Well, indeed, the majority rules, it does indeed increase the sympathetic nervous system. Right? So we get an increase in sympathetic nervous system, decrease in parasympathetic nervous system. That's going to be the result. Go back in your notes. You'll see that once we plug these baroreceptors into the coordinating center, what gets interpreted and sent out now to alert the body or change the body's behavior is an increase in sympathetic nervous system. So what are we plugged into directly with the sympathetic nervous system that is then going to change? Because if we're not plugged into it with the sympathetic nervous system, it's not going to change. So what are we plugged into? Yeah. We are. So let's go to the heart. We're plugged into ventricular myocytes. So what is an increase in sympathetic nervous system stimulation of ventricular myocytes going to do? Increase contractility, increase force of contraction, right. What was the result of that? Increasing a force of contraction. Increased stroke volume, increased cardiac output. Good. In an attempt to increase mean arterial pressure. Now this might not work because we're in left heart failure, but the body has no idea. So it's giving it a go. It's just doing what it's exactly wired to do. Okay, so this is how the body would try to respond. Okay, so indeed we would expect to see increased contractility to increase mean arterial pressure, fixing the problem. Okay, where else in the heart can we go? The SA node, so nodal cells. What's going to happen with sympathetic nervous system to nodal cells? What was this maneuver for? Increased SNS to nodal cells. Increased heart rate. And then what? So increased cardiac output because of an increased heart rate. Excellent. And that would result then in an increase in mean arterial pressure. So that was why the body is wired this way. Okay. We also know that with an increase in heart rate because of that staircase or that trap phenomenon, we get an increase in contractility, increased stroke volume, cardiac output, mean arterial pressure. Okay. Perfect. So where else are we going to go with sympathetic nervous system? Where else are we directly plugged into so that we're going to get something to happen? Smooth muscle in arterioles. Perfect. So vascular smooth muscle, let's go there. So what will sympathetic nervous system, what's the sympathetic nervous system response to vascular smooth muscle cells in arterioles? Vasoconstrict, and why did we do that? Oh, that is. So what was the issue with vasoconstriction here? Why did we do that? We don't know why we did that yet. Decrease volume out of the aorta, so this is a maneuver to increase total peripheral resistance, right? That is absolutely right. Increase our total peripheral resistance, right? We're going to decrease volume out of the aorta, increase volume in the aorta, increase pressure in the aorta, right? So increasing total peripheral resistance is a maneuver to help us with an increase in mean arterial pressure. The body is responding to try to fix the problem. Not because it knows what the problem is, because it has a sensor for mean arterial pressure. Mean arterial pressure dropped, and this is just how we're wired. Okay, so how else are we wired? What else is the sympathetic nervous system plugged into? Adrenal glands, perfect. What are we going to do there? Same thing as all the stuff above, right? So the adrenal glands, we're going to release epi and norepi, and it's going to support all of the things that we've already said, right? Because all of the things we've already said are based on an adrenergic membrane receptor population. So we're going to spit out an epinephrine and norepinephrine. It's going to find the same adrenergic membrane receptor population. Okay, so that really is going to support all of the above that we've got so far. Perfect. Anywhere else that we're plugged into directly with the sympathetic nervous system, or anything else that high pressure baroreceptors are going to do? I had one written out on overhead 10 minutes ago in terms of where we're connected to the sympathetic nervous system. Okay, does anybody want to pick on another sensor? Is there another sensor in here that might be stimulated by stuff that we've messed with right now? We had high pressure baroreceptors. Yeah. So we had an osmoreceptor. So at the moment, we haven't really changed osmolarity. Good thinking. We haven't really changed osmolarity yet, though, right? So unless osmolarity is changed, it's not going to get tweaked, right? Yeah. Increase SNS, increase renin. Brilliant. And so now you got to know the flood of hormones that are going to come out based on an increase in renin maneuver. Okay? So indeed, we can go to the kidney. Based on direct SNS innervation into afferent and efferent arterioles. With an increase in SNS, I'm going to get an increase in renin. Okay, so what is the result of that increase in renin? So this is the whole body calling for it. Okay, so now we have systemic increase in renin. So what does renin do? Increase GFR. So fill in the space for me there. Increase angiotensin 2. Now we're talking systemically, right? So the whole body, we've got whole body angiotensin 2 going on, right? Increase in angiotensin 2. Angiotensin 2 was a vasoconstrictor of afferents equal to efferents. So not necessarily a change in GFR here, right? But a decrease in renal blood flow. So we're just going to stop sending blood to the kidney. All right, we can't lose it if we don't even let it go by the kidney. All right, so this is a maneuver to decrease renal blood flow, to try to keep all the fluid that we have in the system, okay? Any other effect of angiotensin 2? For this, we'll have to dip back quite a bit. Angiotensin 2, we talked about being a systemic vasoconstrictor, okay? So angiotensin 2 is a vasoconstrictor systemically. So this is going to be a maneuver to help us with an increase in total peripheral resistance to increase mean arterial pressure. Okay, so now we're bringing on our hormones. We stimulated or we had a change in total peripheral resistance based on direct nervous innervation, and now we're bringing the hormones on board, okay? Any other places? Give me a piece of paper here. Any other places you'd like to go? So let's stick with Renin for a minute. Yeah. Increase ADH. Brilliant. Renin stimulates ADH, or it's angiotensin 2, right? It's angiotensin 2 that stimulates the production of ADH. So let's kind of go off that guy. So I'm going to increase ADH. What do you want to do with that? ADH. Had a lot of stuff going on with ADH. Yeah. Right, so we're going to increase water reabsorption. There's a lot of spots in between there. Increase water reabsorption. This will increase our blood volume to help increase our mean arterial pressure. Okay, so you can see the whole system is wired to be working to fix the problem. Okay? Anything else? ADH is also a systemic vasoconstrictor, so it's going to be doing the same thing angiotensin 2 does systemically to all arterioles, right? So it's going to help us with our total peripheral resistance. And of course, really cool, what you've laid out here already is the three different time scales, right? So not all of these things would be effective at the same time, right? Anything that's nervous would be milliseconds to seconds. All right, so nervous. Is going to be milliseconds to seconds time scale. Our hormones that you're getting out are seconds to minutes. And then you've started work at the level of the kidney with ADH, right? So ADH will find its membrane receptor population in seconds to minutes, and it will make it more permeable, but now we just have to sit and wait for filtration so we can get back more. That's just going to take time. So when you affect fluid flux at the level of the kidney, you're talking about an hours to days fix to the problem, okay? Okay, so we do have our three different time scales hanging out there. Okay, so that's pretty good. I want you to think about adding on to this example. So let me see. I want you to think about, where are we here? I want you to think about veins. Okay, I want you to think about what changing systemic veins would do, because we are directly innervated with the sympathetic nervous system into veins, and that will help us with our problem. Okay, we did have an effect of mean arterial pressure. And an ADH relationship that looks something like this. So I need you to think about that, how we got that. Okay, think about that line. I want you to think about atrial stretch. You changed venous return. The moment you change venous return, you change stretch, you change atrial natriuretic peptide. Okay? And then you're going to start to, as soon as you change ANP, you change renin, angiotensin 2, ADH. Okay? So I want you to think about atrial stretch. and atrial natriuretic peptide here. So think about, and then, so what I've got, 1, 2, 3. I want you to think about fluid flux. What's happening with fluid flux, and is that helping or hurting our problem? Okay, so I think that once you add that, then we have a pretty good view on what the response of the blood of the body would be to left heart failure. And you can do this exercise with any problem. Mean arterial pressure can either go up or down. It's binary. The body can either do this or the opposite. It's binary, okay? So I'd highly recommend practicing both. Okay, good job today.